This is section 7.3, the discriminant. Today you will be discriminating, and that'll be fine. It'll be okay. So, how do we use the discriminant to determine the nature of the roots of a quadratic equation? We probably should figure out what exactly this discriminant thing is. Well, yesterday you learned the quadratic formula, or you relearned it. The roots of the equation ax squared plus bx plus c equals 0 and are given by this formula. So I've split the quadratic formula into two different equations, one representing the positive, one representing the negative. So the part in yellow is called the discriminant. So d, the capital D you'll see in this section, equals b squared minus 4ac. So that is the discriminant. And what the discriminant does, it tells you a lot about the nature of the roots of the quadratic equation, well, without actually having to solve the equation. So it comes in pretty useful. It's kind of a quick and dirty way to figure out what kind of roots you're looking at without actually going through the whole quadratic formula. So let's see how this works. If your discriminant b squared minus 4ac is greater than 0, then there are two unequal real roots. And if you look at it graphically, you would see two x-intercepts that represent the two unequal real roots. So you see this graph here, and now you see the two intercepts. So those represent the two unequal real roots. If b squared minus 4ac is greater than 0, the discriminant is positive. If the discriminant is equal to 0, then there is a real double root. So there's only one x-intercept, and the graph is tangent to the x-axis at the location of the root. So if you're looking at this graphically, this would be the only point down there. There it is. Finally, if the discriminant is negative, then there are two conjugate imaginary roots. And you can look at the parabola on the graph. You will see it does not intersect the x-axis. Since there are no real roots, there is no intersection of the x-axis. So this is where you can determine the nature of the roots of a quadratic equation. If the discriminant is positive, two unequal real roots. If it's equal to 0, then there's a single real double root. And if it's negative, then there are two conjugate imaginary roots. Alright, on page 318 you'll see the test for rational roots. If a quadratic equation has integral coefficients and its discriminant is a perfect square, then the equation has rational roots. So this is what you'll need to know. If the discriminant is a perfect square, then you're going to have rational roots as opposed to imaginary roots. If a quadratic equation can be transformed into an equivalent equation that meets this test, then it has rational roots. So basically what this means, if you have a decimal or a fraction that you can multiply out to get integral coefficients, then you can apply this test. If you have irrational coefficients like a radical or pi or something, then this test does not necessarily apply. So if you have, for example, a coefficient of negative radical 2x, but you get a perfect square as the discriminant, then you don't necessarily get a rational root. Let's look at example 1. Without solving the equation, determine the nature of this equation's roots. So we have x squared minus 8x plus 5. So all you really have to do is check out what the discriminant is. So remember that d equals b squared minus 4ac. So there's your b, negative 8 quantity squared minus 4 times 1 times 5. And you just do the math. So you have 64 minus 20, and so your discriminant is positive. Since it's positive and it's not a perfect square, then you have two real, unequal, irrational roots. And you will not get rational roots because you don't have a perfect square. So, positive discriminant, two real roots, two real unequal roots. That's the nature of the roots number 1 on page 318. And they're irrational based on the test for rational roots. You have integral coefficients and you do not have a perfect square. So therefore you do not have rational roots. Example 2. X squared plus 10x plus 25 go ahead and try this one. Some of you can probably guess the answer already. So we have the discriminant of 10 squared minus 4 times 1 times 25, which produces 100 minus 100. So your discriminant is equal to 0, which tells you that under number 2, you have a real double root. You also have a rational double root because your discriminant is a perfect square. And you have integral coefficients. D equals 0 is always a perfect square, so you're going to have one real, that is rational, double root. Number 3, x squared minus 4x plus 13. Go ahead and attempt this one yourself. Check the nature of the roots test and the test of rational roots to draw a conclusion. So your discriminant is negative 4 squared, which is 16, minus 4 times 1 times 13, which is 52. So your discriminant is negative 36. Well, if you have a negative discriminant, under number 3, you have to have two imaginary conjugate roots, which makes sense, because if you have a discriminant that's negative, that's the part under the square root in the quadratic formula. So by looking at it right there, you notice that you're going to have an I in the answer because you have a negative in the square root. Number 4, we have x squared minus 7/3 x plus 2/3 equals 0. Go ahead and try to do this one yourself. Most of us don't like fractions. See what you can do to get rid of them. So I multiplied every term in the equation by 3 to get 3x squared minus 7x plus 2. So now you have integral coefficients, which will really help when you deal with the tests for rational roots. So let's apply the discriminant test. You have negative 7 squared minus 4 times 3 times 2, which is 49 minus 24. And hey, we have a perfect square. 25 is a perfect square. So you're going to have to be able to identify perfect squares pretty quickly. So because you have a perfect square and that the discriminant is positive, you have two real unequal rational roots. Because the discriminant is positive, you have two real unequal roots. And because the discriminant is a perfect square and that you have integral coefficients, those roots are rational. So you have to apply both tests to kind of see what type of roots do you have. Number 5, x squared plus 4 radical 2x minus 8. Notice that the 4 radical 2 is the coefficient of x. The x is outside the radical. So go ahead and figure out what the discriminant is, but keeping in mind now that you no longer have coefficients that are integers. So you have the discriminant equaling 4 root 2 squared minus 4 times 1 times negative 8, which produces you a discriminant of 64. So you have a perfect square. So because your discriminant is positive, you have two real unequal roots. However, because you have an irrational coefficient that you cannot express as a fraction or an integer, the roots themselves may not be rational. In fact, they probably won't be because you have an irrational coefficient. So remember, the test for rational roots only applies if you can express the equation with integral coefficients, which we cannot do here. Alright, we also have example 6, and this comes straight out of page 319 in your book. So, we have an equation, kx squared plus 12x plus 9k equals to 0. And it will have different roots for different values of k. And now what we're going to do is look for values of k for which each equation has the following type of roots. So, we're going to use the discriminant formula, plug in the values of the coefficients just like we did before, and see what happens. So let's start with a real double root. For a real double root, looking at number 2 of the 3-pronged test, your discriminant has to be equal to 0. So let's set our discriminant equal to 0. We have 12 squared minus 4k times 9k equals 0. This k is the a value, 9k is the c value. You put that all together, you get 144 minus 36k squared equals 0. Now let's solve for k. If you separate the two values and divide by 36, you get k squared equals 4. So when you take the square root of both sides, make sure you include both the positive and negative. So k would have to equal plus or minus 2 for it to produce a real double root. Either k value will produce a discriminant of 0. What about for two different or unequal real roots? So what you're going to have to do is set your discriminant to be positive. And again, solve just like before. You know that 144 minus 36k squared is the value of the discriminant. Now it has to be positive, greater than 0. So you get to the same point where now you have k squared is less than 4. And when you take the square root of both sides, make sure now you have the absolute value of k. Because remember, the square root of k squared equals absolute value of k. So the absolute value of k is less than 2. From what you remember about absolute value, this means that the value of k has to be between -2 and 2. So any k value between -2 and 2 will produce two unequal or different real roots. Finally, what about imaginary roots? This means the discriminant has to be less than 0. So 144 minus 36k squared is negative or less than 0. So k squared has to be greater than 4. Again, taking the square root of both sides tells you that the absolute value of k is greater than 2. So now again, by the definition of absolute value, this means that k either has to be less than -2 or greater than 2. So make sure you will be very careful about having to solve for roots. If you have a k squared and an inequality, make sure you have the absolute value and you have the right term. So here it's OR, and for the previous one, k has to be in between -2 and 2 to get two real unequal roots. So this is how you do these problems, and you'll see quite a few of them on the homework. So let's take a look at our summary. If you have an equation in the form ax squared plus bx plus c, where a is not equal to 0, and you have first rational coefficients, and this is a little wrinkle on what the book does. If your discriminant is positive, you're going to have two real different or unequal roots. If your discriminant is 0, you're going to have one real and rational double root. If your discriminant is negative, you'll have two imaginary conjugate roots. If your discriminant is a perfect square, then it's going to have rational roots. And if your coefficients are irrational, like we had in example 5, even if your discriminant is a perfect square, this doesn't necessarily mean that the roots may be rational. Finally, we didn't cover this, but if you have an imaginary coefficient, you can throw all these rules out the window because none of them apply. This rule for the discriminant only applies for real coefficients. Alright, that's it for 7.3. If you have any questions, please ask me in class or via email. Most of you guys don't ask questions, and you have questions in class, so that's fine. You can save them for then. But if you have any lingering and pressing questions, please ask me as soon as you can, and I'll try to get back to you.